All right, here we go. There's Jose's favorite sport.
No.
Oh, you don't like soccer anymore?
Racist.
It's because
It's he's Mexican.
why can't it be my favorite sport?
Because he says he always plays soccer.
I like soccer.
You play tennis. Okay, that's your sport. Okay, all right. One of the things, now this even goes on to American football. We remember the New England Patriots not this past season, but the season before, they got in trouble for their football not having the right pressure inside of it.
Tom Shady.
All right. All right. Okay, that's an interesting name. Seeing that's my team. So, anyways, if you look at it in a soccer or regular football, you need 0.6 atmospheres and no higher than 1.1 atmospheres. Okay, what is an atmosphere? Anybody know what an atmosphere is?
It's where it's like what covers the earth.
It is. But what's an ATM in regards to this kind of atmospheres? You've already learned this. It's a measure of pressure. We've already looked at that a little bit. What were the things that are equal? 1 atmosphere, 101.3 kilopascals, and so if we look at it, let me just write that out for you. So types of pressure is 1 atmosphere is equal to 760 millimeters of mercury. You might be. I don't know if you can or not. Equals 101. Oh, sorry. Kilopascals. So if you know those 3 things, you know the 3 things of pressure, and you can basically go from one to the other. All right? Okay, this is a good question to think about. Why do you think it's easier to compress gases compared to liquids or solids? Somebody want to give me an idea of why that's possible? Marco.
Because they're so spaced out that if you were to compress them, you're like, I don't know.
There's like
Yeah.
there's room between the gas particles. Why isn't that true with liquids and solids?
Like
There's a
tightly packed.
They're tightly packed. Well, actually, okay, very good point that you made. There's more attraction between them. There's actually theoretically attraction between gas particles, but that's why we talk about ideal gases, because they're so far apart, we don't get them attracted until we really get them really close together. So what happens if you keep on compressing a gas? Does anybody know what happens if you keep on compressing and compressing? No, it doesn't. That's a good answer, but no, it doesn't. Right. That's because the balloon isn't strong. If you put it in a strong container, that's not going to pop like a balloon does. And you keep on putting pressure. What do you think is going to happen eventually? What are you doing? You're moving those gas particles closer together. So if you move them closer together, think of what Sarah just said. We are having a lecture right now. Okay, so what we're doing is we're basically having, we bring them closer and closer together, so there's attractive forces. If there's more attractive forces, things that are close together will become what? Liquid. So when you compress something so much, eventually it turns into liquid because those interactive forces are close enough. So that tells you how far a gas has to be, apart for it to be compressed so much. It has to be really, really close together before it turns into liquid. So that's one of the reasons why gases are easier to compress than solids or liquids. The solids and liquids are already very close together. There's already attractive forces that are acting between them, and they stick together. Okay, the definition of compressibility is how much a volume of matter decreases under pressure. Okay, there's a picture that would have been appropriate for the test. Okay, there's the airbag filling with nitrogen. Okay, and we also know that there's another chemical in there, so the sodium doesn't burn you. Okay, we've already talked about that. Okay, remember that the gas particles themselves, okay, are very, very small. Okay, so if you think of some gas particles here in a container, You might want to have one here. You might have one here. Might have a dot there. They're really teeny, okay? But there's a lot of empty space in between them, so the interactions aren't going to be that great. So we kind of consider them almost having no individual volume, okay? That's a very important idea, Ronald. Okay, if I will give a grade on participation today if you're paying attention. Okay, so they're very, very close together. I mean, they're very far apart, and they're very, very tiny. Okay, so we usually don't consider this little dot volume. We consider the whole container volume when we look at the volume of the gas. As we compress them, okay, as we compress them, what happens is this. They start getting closer and closer together. So those little volumes now become important, and then you get a little drop of liquid. Okay, that's what happens when you compress them. And as we mentioned, the distance is much greater than with liquids or solids. All right, so now we have two different containers. We have a container that has a large volume and a low pressure. And then we have a smaller container where the same number of particles are in that smaller container, but look at, they're closer together. So they've been compressed. So what causes air pressure? Who can tell me what causes air pressure? Does anybody know what causes air pressure in a container? The pressure?
Pressure of air.
Well, yes. But what's causing that pressure?
Movement.
Movement is part of it. So what happens when it moves? What's the likelihood of it to happen? Okay, what do you need? If I go like that and apply a force, does it really have any pressure? It has to hit something. So what does the gas particles hit in this picture?
The container.
The container. So hitting the side of the container, and also to a certain degree hitting each other, but mostly hitting the side of the container builds up pressure. If you have a smaller container and the same number of particles as a larger container, which container will have the higher pressure? Smaller, because it's more likely to hit the side, because it's smaller, it doesn't have as far to go. So it's just very logical that you would have a stronger pressure in smaller containers with the same number of particles. So when you compress air, the pressure will go up. So this one here will have more collisions. So it's going to have a higher pressure. This one will have less collisions. And this goes back to chapter 13, where we talk about the kinetic molecular theory. Okay? So the bigger the volume, the less the pressure for the same amount of substance. All right. This is what we've just been discussing. So if air is easily compressed, wood is not. Wood can be compressed. Why can wood be compressed? Does anybody know why wood can be compressed? It can be slightly compressed.
Like when they burn it to ashes.
Because it's a solid.
Well, it's a solid, but I mean the fact is most solids can't be compressed very much at all. But wood can be. And you got it. This is more thinking about biology than chemistry. It could be dry. It can still be compressed when it's dry, but you're on the right track.
Oh, they have the.
There's air in it because remember there's the cell walls and the cells, and there's little areas of air. So there's some gas contained in it. I mean, we can say that it's a solid, and that's what the answer is going to come out with. But we need to think beyond that. Wood we know can be compressed because if you go to the beach and walk on the boardwalk, sometimes you'll see artificial wood and sometimes you'll see compressed wood. That keeps termites from getting in there because it's all close together. All right, so let's see what they say. All right, so they give us the answer we expected, that it's very hard to compress wood, but ever so slightly wood can be compressed. It would have been better if they chose something maybe like a metal or something like that that's very, very hard and doesn't have as much airspace in between. Okay, what are three factors that affect gas pressure? Okay, all right. We're going to be looking at these four terms. Okay, we've already mentioned pressure. So let's think about each one. Okay, we're talking in regards here.
Are you still doing play posits or no?
Yes.
For this lesson too.
This is no, because we're doing it in
14.2,
class. Okay, so pressure is in kilopascals or atmospheres or millimeters of mercury. So these three other parts, number of moles. Okay, what Sarah Zalea, what is number of moles about? I mean, what's another word for saying, if I'm talking about if the number of moles influence it, could you make that more general for me than say to say moles? What is moles a measure of?
Atoms.
Not mass, atoms. So it's basically quantities. Atoms are molecules, right? So what we're saying is we have an increasing amount of molecules or increasing amount of atoms. Okay, volume. Volume, we've already showed how volume increases pressure. Which type of volume? More volume or less volume will increase pressure?
Less.
Less volume increases pressure. So what kind of mathematical relationship would volume be with pressure? What kind of mathematical, if it goes down when volume goes up and goes up when volume goes down, what kind of relationship is that? Indirect, inverse, okay? So that's going to be inverse. Okay, let's think of temperature. Okay, if you heat something up, what happens to the movement of those particles? They speed up. And what are they going to do to the walls? Hit it more frequently, so what's going to happen to pressure? It's going to increase. So what kind of mathematical relationship do we have in that case? Direct relationship, okay? And so, okay, I didn't ask about the number of moles. Okay, if we increase the number of particles, increased pressure, because if you increase the number of particles, there's more particles to hit the side of the wall, so therefore it's going to be more than something with less particles. Makes sense, right? So you've got temperature and number of particles will increase that. So let me ask you one other question. Okay, if I tell you these four things are related, okay, in some way, and now I increase the pressure, what must happen to the volume? It must decrease. So if I know what happens to the pressure, I can predict what will happen to the volume. If I increase the pressure, what happens to the temperature? It increases because it's a direct relationship. If I increase the pressure, what happens to the number of particles? Must be increased. So those mathematical relationships we're going to use in this chapter. Okay, so you've already answered that general question. So you have the general idea based on the kinetic molecular theory. Yes, Sarah.
You say maybe that the pressure increases, the volume doesn't necessarily have to decrease, maybe just like the number of.
Well, if you have, okay, for the idea is the two things are interrelated. Okay, so if the pressure increase, the volume of that same amount of gas, you have to look at the, you can't look at it, you have to look at just the relationship between those two things, keeping the other ones constant.
Okay, just keeping the others constant.
Right. In other words, all those things are usually happening at the same time, so we won't be able to predict exactly what happens because there may be influences from the other things too. So we can mathematically look at when all the things are changing, the net effect, but we can't predict it as well unless we're holding other things at constant. Good question. All right, this is what we just said. And we just did this. All right, so let's look at an example. If you inflate an air raft, okay, what happens to the pressure inside the air raft? Obviously, it's going to what? Increase. So if you, how many people ride bicycles? I ride bicycles all the time.
What are my
Okay.
cars?
Okay, and every once in a while, my tire has less air in it. Like today, if I go to my bicycle, it'll probably have less air. Why will it? It doesn't really have less air in it.
Less pressure.
It has less pressure. Why would it have less pressure today than yesterday?
Which because the air comes out. The air comes out
Because
from
you
the
wrote it.
No. What's different from yesterday and today?
The heat.
Yes,
The
but
temperature.
the temperature is lower today. So that same amount of air that I put in a hot day
Oh,
is
then
going
it'll
to
expand.
be compressed, and so I mean it's going to be it's
No,
gonna-
on a hot day it's
yeah.
gonna be expanded.
right. So it's not going to expand the rubber of the tire as much. So it's going to be less. It's going to fit in a smaller space. So it's going to be soft. Okay. All right. So the air pressure is going to change based on temperature, and this is something that you really can use very often. Okay. Take some notes. Okay. All right. All right. So again, as we mentioned about collisions, this is kinetic molecular theory. All right. So kinetic molecular theory states that things move faster and they have collisions. All right. So collisions theory is going to be increasing pressure. Okay. Why is that important for the raft? If you're going to go out rafting, why do you want it to have good pressure on the sides of the
So
raft?
it
So,
doesn't
like-
deflate.
In the middle of the
And it can hold people up, right?
Yeah.
Yeah, because that's really important. So something that we use.
Whitewater rafting. So.
Okay, the other thing we're doing as we put air in, besides giving, the more air we put in, the more particles we have. So that's going to help us increase the pressure. All right, so here we are adding air to container. First, we put some air in. It's only 100 kilopascals. The more we put in. So what are we looking at? We're looking at number of particles. This illustrates what we talked about when we said we increase the number of particles, the pressure will increase. So this is an example of a direct proportion. So when N increases, P increases. When N decreases, P decreases. Okay? That's what that's showing. All right, here's Danny's favorite thing right now.
What? Little girls?
Look, this is all being recorded, so you will have your voice for posterity on YouTube. So, all right.
Now everyone knows you're a little girl.
All right. So you have 600 kilopascals, and this container can't handle that, so it blows up. Okay, that's why. Okay, how many people have ever seen a factory with all those big, metal structures, and sometimes you might see some fire coming off of them, like an oil refinery. Okay, or even FPL's nuclear plant.
Oh, like a candy factory?
Did you say candy?
Maybe, I don't know if the candy factory would be the best
No, you didn't.
idea.
In Tennessee.
Okay, so it's I'm thinking more of a big oil refinery. Candy factory, it could happen to. Okay, so a candy factory, it definitely could happen. All right, but what happens is when a chemical engineer comes along, one of the things they have to realize is the materials they use are going to be probably forced to have very high pressure in them. So if they choose something that's not that strong, they can have an explosion, which then if they have this hot oil going out or starting a fire if it's gasoline. So it's very important to know what the pressure stability of your container is. All right. So in general, if the container is pushing out in one direction, what's pushing in the other direction? It's right there if you read it.
The air pressure.
The air pressure is what is pushing on the outside. So if you go to outer space, what's the pressure outside? If you're an astronaut, what's the pressure outside of you?
Nothing.
Almost nothing. Pretty much we say it's nothing. Okay, what's the pressure inside you? Well, yes, but generally, what's the pressure inside you?
There's a lot of pressure inside us because there's Just so his blood flowing.
Oh, there's like, you know how you can breathe? There's like air in it.
Well, there is. In general, your pressure inside of you is about the same as the outside pressure. Okay, we can probably stand maybe about twice the normal sea level pressure. Okay, but if you go underwater and keep on going underwater, that's why a submarine is they have to be very careful with a submarine, because when they first started making submarines, the pressure really low is bigger than the metal on that. So what is it? It's like a tin can. If you go like that to tin can with lots of force, it collapses, right? Because the outside pressure is greater than the inside pressure. So that's one of the things that you have to have the two things. Yes.
Does our pressure have to do with blood pressure?
Well, that's a little bit different. That's only one part of what's going on in your body. I'm talking about, you also have your skeleton, which is bones, which is kind of acting as like the container does. That supports a lot of it. That's when you start breaking the bones, that's what the problem is. Okay? But you also have your lungs, okay, which is filled with air, and you're taking the air right out from the atmosphere, so that's where your air is definitely the same. Your blood pressure is just the flow through your veins, which is a different sort of thing. Because if you think about it, air pressure is 760 millimeters of mercury, and you're looking at somewhere in the 120 millimeters of mercury going this way, and then when it's at rest, maybe less than 80. So your blood pressure is a lot less than atmospheric pressure in measuring it.
So like if we're just like suddenly placed in an area of very low pressure, saying that like our bones would like crack. And we
Not
would,
low
like,
pressure.
Oh, high pressure.
High pressure. Yeah, low pressure. What's going to happen if you're in very, very low pressure in outer space? Since you're going to expand until you go boom. Okay? That's why if you ever see a astronaut movie,
Oh, what was the Mars? You know,
The Martian.
Sage.
That's called the Martian.
No, it's not Mars.
It's called the Martian.
Wait. The one with Matt Damon, right?
Okay, so if the pressure of the gas is higher, the gas will flow out of the container. Okay? So that's where you get your explosion.
Oh, yeah, it's called Mars.
All right, here's an example of something you use all the time, an aerosol can.
That's a great
Okay, inside the can, you have pressurized liquid that has gas above it, okay? So that gas, we call it the propellant, okay? So in your can of spray paint, when you're going to paint the walls of Winwood, okay, all right, it's going to have you know how you shake it up with that you hear that ball in it kind of thing, to mix it? But there's also air in it of some sort at a higher pressure. Okay, when you press down, it pushes the paint up through the opening, okay, and it makes a fine mist, all right? But that's because the pressure inside is higher than the outside pressure, okay? That's why if you read those cans, they say do not incinerate
Or do not put
and do not puncture.
So those can only bring like half of paint?
Well, it's not full paint, yes. I don't know how much the ratio is.
I pay like $9.
Yeah, but it wouldn't come out. They have to have more. It wouldn't come out.
Yeah, but then the bigger cans.
Okay. If we look at volume again, okay, remember volume? Well, that's true. I want to say pressure. Let me do it this way. It's easier to see it this way. Okay, I should say proportional. Let me do proportional. All right, so volume is proportional to the inverse of pressure. All right, so what I want to say is that's a way of saying if volume increases, pressure decreases. Yes, I know. I can change that.
Wait, what's the one?
I know the one is because it's the
Oh, it's an I?
VA equals 1 over D, right?
you just run.
It's inverse pressure.
Exactly.
Except for I.
No, idiot. Neck, no nothing.
All right,
Mr.
so
Baldino, is that a 1 or an I?
that's a 1.
Yes, you can.
Don't hit him, please. Okay, 1 over P means inverse, so it's inversely proportional. The more the gas is compressed, the more pressure. We've already talked about that. The less, obviously the less, it's going to be the opposite.
Yeah, that's how I said sorry.
You want me to write that again? Got it? All right. Okay, I can wait. Okay. Now, we already said if we increase the volume, it's going to decrease the pressure. So remember, it just goes the opposite way. Now, this is a very important thing. If the volume is doubled, the particles can take up twice as much, they take up twice as much space. So that's going to cut the pressure in half. All right? So if V, oops, I'm sorry. Get the pen. Okay, so what this is saying is if volume is increased by 2, it's times 2, the pressure is going to be decreased by 2 or multiplied by a half. Okay? Make sense? Questions? Okay, so in this picture we show how we often decrease volume. We use what's called a piston. In your car, there are things called pistons. Does everybody know that?
Yes.
Okay, so the pistons are what helps drive your car because there's hot exploding gas. Okay, your gasoline gets heated up, it gets exploded, and this piston changes, and that energy is converted into movement. All right, so that's kind of what's happening anytime you use a piston. So by using that piston, you can change the volume. So by pushing down, you're increasing the pressure. By pulling up, you're decreasing the pressure. Okay, now we can talk a little bit more about temperature. Okay, we know what happens when a gas is heated. Okay, what happens to the particles when a gas is heated again?
They start to move faster.
They move faster. Okay, so if it's cold, they might move. I'm going to put a little arrow. Okay, when it gets hotter, they're going to go further. So if they're moving faster and going further, they're going to hit the walls more frequently. Okay, so the particles' kinetic energy increase, they move faster, and they hit the walls of the container with more energy and also more frequently. Okay, so if we look at this, we see a rise in pressure with a rise in temperature. Okay? And then if we heat it too much, we can also have an explosion. Another thing to think about when you're building a factory, if you're a chemical engineer, is that what temperature is your reaction occurring in these big plants? Okay, if it's too hot, you're going to explode the plant, and this has happened. Okay, this has happened. When I was your age, a big chemical explosion occurred in India with a toxin that killed the whole town almost.
How many people died?
Thousands. Okay. Okay, so these things are, you think, oh, well, this is just something I need for chemistry class. These things are what you depend on, that someone has learned and knows how to do that. Danny, these are things that people have learned and you depend on that they're going to do it right. For instance, at the nuclear plant, which is only about 10 miles from here, 15 miles. Okay? Yes. You want to make sure that whoever designed that plant knows that when the heat gets really hot, that it cools down so that it doesn't blow up the plant and puts radioactivity into the atmosphere around us. Okay? So there are fail-safe things to make sure that doesn't happen. But what did they use? They used exactly what you're learning here. Okay?
Can you tell him to give me back the charger?
It's my charger. Daniel, right? That's my charger.
Jose, you're being recorded. How does the pressure of a contained gas change when the volume of the gas is increased? A, B, or C? Okay. Very good. Okay, Jose, we're back on soccer again.
That's racist. Okay.
No, because you're a soccer player. Why is that picture there? Because we're talking about the inflated soccer ball. Remember we talked about that at the beginning of the thing? Okay, which do you think would travel farther? The one that's inflated higher or the one that's inflated less? Based on what we've been talking about. Inflated higher because it's got more pressure. All right? Okay, what might happen to an overinflated soccer ball if you kicked it too hard? That's very good. Okay, the ball might burst when it's kicked. Very, very good because you're putting too much pressure on it. All right, so pretty much that summarizes our introduction to chapter 14. All right.
He just took your charger.